Welcome to lesson 50, equations in quadratic form. Now that is deceptive in a way because you might just be thinking, oh, quadratic equations. I've done quadratic equations before. You use the quadratic formula, yay. But this is actually a little bit deeper than that. Equations in quadratic form, we're talking about equations that are not quadratic. They are not quadratic. But by doing a little clever manipulation of variables, and we'll see how that works, we can actually take an equation that is not quadratic and turn it into something that is quadratic, which is good because then you can use the quadratic formula and solve it. So anyway, it's kind of a large process, but let's kind of sneak up on it. First, a blast from the past. First, let's just solve this equation in a way that we know how. Just by factoring. So we've solved equations by factoring in lessons 47, 48. How would you factor this thing? It's three terms. It's a trinomial, so usually you think in terms of some kind of unfoil type of a thing, right? So then you say, well, x to the fourth, how would I break that up? I could break it up as x squared times x squared. And then I've got a negative 36. How do I break that up? And that's where you do a little bit of the, monkeying around, guessing and checking until you get something that works. You want to break up the negative 36 until you get two numbers. That gets you a positive 5 in the middle when you work out the inner and outer products. So 9 and 4 should work. I'm thinking a minus 9 and a plus 4. How does that work? Let's just double check that worked. So that's x to the fourth, of course, plus 4x squared minus 9x squared. Notice the two middle terms wouldn't... Oh, that didn't work. That's giving me a minus 5x squared. That's not what I want. I want a plus 5x squared. Well, that's easily remedied. All I got to do is take my minus and plus and switch them around, and that should work. Let's do that. Switch. Okay. So which one did I do? This, go this way, right? Right. I better double check that again just to be like really safe. So I got a plus 9x squared here, and I got a minus 4x squared here, and when you add those two together, you end up with the plus 5x squared in the middle. Okay, cool. I did it right. That's good. It's always good to start by doing it right. So we factored it, and we can keep factoring it because remember, well, for one thing, a difference of squares. You can just do this, right? The old x minus 2, x plus 2. And remember, we have a trick for doing a sum of squares. It's not x minus 3, x plus 3. It's x minus 3i, x plus 3i. And I invite you to FOIL that out if you need to double check that really works. But it works. So we've got this completely factored now. And so we can read off in 4 places 4 solutions. We could have either a positive or a negative. I'll put the real number first. We could also have a positive or a negative 3i. 4 solutions. A degree 4 equation with 4 solutions. Life is good. So there was nothing fancy there. We've seen that before. The old, factor completely trick in order to solve. But I want to take it. I'm going to do the same problem again. I like to do that sometimes. Anchor something new on something familiar. You believe these solutions, so let me show you a different way to get them, and when we get them you'll have to believe them because you know they're true. So anyway, solve by using a switch of variables. What am I talking about? Well, earlier when I said we're going to take equations that are not quadratic, and let's write that explicitly right here. This is not quadratic. Quadratic has to have x squared. This does not have x squared. It's not quadratic. It's not a quadratic equation. But I'm going to turn it into one. How? What you do is you take this part and you give it a new name. I'm going to call it, come on pencil, keep up. I'm going to call it define. I'm going to write a little more neatly. Define. I'm going to take that x squared and I'm going to rename it, and you can use whatever letter you want. I've been using u and w. Some people use theta, whatever you want. I think I'm in the mood for a u today. So I'm going to say x squared is equal to u. This is now u. Okay, it's just a different letter, that's all. Well, if that's u, what's this? Notice if you take x squared times x squared, you get x to the fourth. In other words, if you take u times u, you get x to the fourth, right? Let's put that in parentheses here. So if you square both sides, x to the fourth, man, my pencil is just bugging me today. Okay, so anyway, if you square both sides of that little mini equation, u squared is the same as x to the fourth. So what we've got is we've got a transformed equation. New equation. Instead of writing x to the fourth, I'm going to write u squared 5 times, instead of writing 5 times x squared, I'm going to write 5 times u, and then minus 36 equals 0. And this is a quadratic equation. And that's what we're aiming for. This is what we mean when we say an equation in quadratic form. This one is not quadratic, but you can reshape it, massage it, and make it look quadratic with a little switch of variables going on there. Okay. So what do you do now? Now that you've made the equation into a quadratic, we can now solve this one by factoring u, let's see now, I'm thinking u plus 9, u minus 4 equals 0, right? That'll work, won't it, if I FOIL that out? Okay, and so I've got two solutions. U equals negative 9, u equals positive 4. Now there's only one thing. Those are not the solutions to the original equation. Those are the solutions to the new equation. Solutions to new equation. Okay, so now we'll switch colors, switch modes here. So, to get solutions to the original equation, take x squared equals u and use our solutions u equals negative 9 and 4. In other words, we figured out what u is by solving the new equation. U is either negative 9 or 4. Well, here's what u is. That's how we defined it when we did this whole switching of variables in the first place. We said, well, u is going to be the same as x squared. X squared is the same as u. So you take that and you use the negative 9 and the 4 to say, oh, so either x squared is equal to negative 9 or x squared is equal to 4. And in this case, I'll just take square roots of both sides. Remember the plus or minus idea. And here's where you're getting your solutions plus or minus 2, just like we had before. Pardon me. And then remember, if you take square roots of both sides here, because you're taking the square root of a negative, you're going to get an I, right? But anyway, plus or minus the square root of negative 9, which is going to give us plus or minus 3i. And so if we scroll back up, you say, yeah, those are the same two solutions we got before. Cool. So take a look at this for a little while. What just happened? We had this equation, which was not quadratic. And even though we didn't have to, we could have solved it the way we did up here. We could have. We didn't have to do this, but we did it just to see how it works. We decided we would take the x squared and give it a new name, u. I'm going to use the letter u today. Take that and take that chunk of stuff, in this case just an x squared, take that chunk of stuff, give it a new variable name, u. If that's u, then that's u squared. And so u squared plus 5u minus, I have a quadratic equation now with this new fangled variable that I just defined. That equation is, the whole idea is that the new equation should be easier to solve because it's just quadratic. So I just solved the new equation. You just got to remember that once you've solved the new equation, what you're after is solutions to the original equation. So you have to go back to this part, the part where you said, well, u is x squared. And you use that with your solutions in order to get the x. All right, now let's do it on a bigger equation. See, this equation, you might be a little more motivated to say, you know, do I feel like squaring this out, and then I'll have to multiply the 8 into here, and then I'm going to have an equation that has denominators, and then I'm going to have to clear the denominators, and or here's another idea. You see this big chunk of stuff? You notice that it's repeated, right? That's kind of your tip-off that this could work. Let's just say that that has a new name. We're going to give that a new variable name. Instead of x plus 3 over 2x minus 5, we're going to say that that is the same as u. And so this, of course, is a u with a square on it. So here's my new equation. U squared plus 8 times u plus 12 equals 0. Now that's a happy equation. That's a happy chappy right there. Let's solve that thing, man. Hey, man, it's a quadratic. We could probably factor it. That's usually what happens. Let's see. Two numbers that multiply to 12 and add to 8. That would be 2 and 6. U plus 2, u plus 6 equals 0. Look how fast we come at solutions to this equation, huh? This is why we like the new equation, because it's easy to solve. That's why we like it. This was going to be a chore and a half to solve that. Oof. Why do a chore and a half when you can just do like a quarter of a chore? See, that's better. Anyway, here comes the hard part. Well, not the hard part, the important part. Now, get solutions to the original equation. You use what you said. Whoops, I shouldn't be circling the 8. You use, whoa, let's do it this way. You use what you said u was. U is this stuff. So you say, okay, so x plus 3 over 2x minus 5. That's what I defined as this u variable. And this is saying that u could be negative 2. And this other one over here is saying that u could be negative 6. So take that x plus 3 over 2x minus 5, set it equal to negative 2, set it equal to negative 6. Solve those equations. When we solve those equations, we've solved for x and we're good. So, how do you want to solve these equations? First, I'm going to put a dividing line here. In fact, you know what I think I'm going to do? I think I'm going to need more space. I'm going to move this one over and up. I'm going to say go over there and solve that one, go up there and solve that one. Okay. So this one, how am I going to solve this one? What I would encourage you to do is whenever you can, think of things as proportions, right? If I take that negative 2 and I put it over 1, all of a sudden I got something that looks a lot like a proportion. So you can do cross products. I love that. So let's see now here. If I do cross products, x plus 3 times 1 is, well, that's x plus 3. And that has to be the same as the other cross product, which is negative 2 multiplying a 2x minus 5. So what do I got? I got x plus 3 equals a negative 4x plus a 10. If I add 4x to both sides, that'll become a 5x. And if I subtract 3 on both sides, that'll be a 7. And so what I'm getting here, that's an arrow, what I'm getting here is x is 7 over 5. And that's one of my solutions. Cool. Let's do that same song and dance over here. Take that negative 6, think of it as over 1, and say, yeah, man, I dig proportions. So the x plus 3 times a 1 going on the one diagonal is x plus 3. And then the negative 6 would have to multiply this on the other diagonal. Okay, start distributing and stuff. Negative 12x plus 30. So if I add 12x to both sides, I get a 13x. And if I subtract 3 on both sides, I get a 27. And so x is equal to 27 over 13. And so I've got two solutions. X could be 7/5, x could be 27/13. Those are both solutions to this original equation. So this is the value of the switcher variables, if you will. This equation here, well, I suppose it would as a quadratic, really. If you did, square this out and all this other stuff, I'm pretty sure you would have ended up with the quadratic eventually. But anyway, the method was still nice. Make the switcher variables. Then you end up with a really nice quadratic. Whoops. A really nice quadratic, or this one was, a really nice quadratic, which you can solve really quickly. And then you take your solutions to the new equation, bring it back to how you defined u in the original equation, so you can have the solutions to the original equation. Example 3. Now this is an example of an equation that is definitely not a quadratic equation. It's not a quadratic because even though it starts with x squared, having this square root here really messes it up. So that's not a quadratic equation. Let's just write that right away. Not a quadratic equation. And then here's the other thing. Remember the last lesson we were solving radical equations. How did we solve radical equations? We would go like this. We would isolate the radical. So if I take the 6, if I subtract 3x on both sides, and I subtract x squared on both sides, right? And then we would square both sides. Well, you're running into some trouble here. Do you really feel like taking this side and foiling it? Or this is more than FOIL, right? It's 3 terms times 3 terms. Do you really want to do all of this? You're going to have x to the 4th terms. You're going to have x cubed terms. You're going to have x squared terms. You're going to have x terms. You're going to have a constant term. That's going to be a mess. So let me erase all of that, because that's kind of, what do you want to call it? Hideous? Hideous might not be a bad word. Not quadratic equation. Not really. Maybe it is, but I don't think so. Not really solvable by isolating radical first. So what I'm trying to do is I'm trying to motivate this one and say, well, sometimes you just really do have to use this new method, today's method. Switching the variables. How might I switch variables to make this equation look like a much nicer equation? This equation is not friendly. Trying to solve this directly, not going to be fun. So what might I do switching variables? Give something a new name to make the equation look nicer. So you hunt around for patterns that repeat. So you say, well, here's an x squared plus 3x, but then here's an x squared plus 3x again. Notice the pattern is repeating. So I'm going to maybe erase that, and I'm going to get out my green, which is kind of like thinking color or something. Notice the pattern. X squared plus 3x repeats. Okay, that's the first thing you note. Okay, now think a little bit further. We would like it to be squared in one spot, not squared in the other spot. So let's try, and there's different ways you can approach it, but let's try. If I set this square root part, okay, I'm going to circle that because that's going to be my definition. I'm going to call that my new variable u. Well, notice that if I square both sides, the left side would become this, and the right side would become this, right? This is kind of what you're trying to get at here, right? So I suppose I don't need a box for that, but if I let u be this part, the square root of it, x squared plus 3x, then this part becomes the square of u, and that's awfully convenient. So our new equation will look like this. Again, this part becomes just u squared. This part, the square root of that stuff, becomes just u equals 6. There's our new equation. Doesn't that look like a nicer equation to play with? I think so. So what I'm going to do is, I guess I'll subtract the 6 on both sides right away. That way it looks like a quadratic in standard form. But anyway, that's a quadratic. And there's where you put a nice big happy face. Quadratic. We can solve that. We can solve that by factoring, in fact. Break up the u squared as a u times u. Break up the 6 as a, let's try a 3 times 2. Trying to get a positive u in the middle. I believe that's how we would do it. So notice I got a plus 3u and a minus 2u gives me the plus 1u. So that works. That works. So I got my solutions for u right away. U equals negative 3, u equals positive 2. Those are my solutions for u, for the letter u. Now, got to go back and get x. We're not actually asked to solve for u, right? We're asked to solve for x, right? This equation has x. They're asking us to solve for x. We have to go back and get x. So back to x. So how do you do that? You come back to, this is where you defined what u was. This is your link between u and x right here, right? You said that when x squared plus 3x is in a square root, that's the same as u. So what we got here is we got square root of x squared plus 3x. I gotta move my hand or something. X squared plus 3x is equal to negative 3, or radical. X squared plus 3x is equal to 2, right? So just take that solution, try both of them. Now this one here if you're alert to this negative here, we can solve this one very quickly. There is no solution to that one. What? Again, this has been with us for a while. The idea that the radical symbol means the principal or positive root. It's the positive root. The positive root cannot be -3 if it's the positive root, right? It's the positive root. It's -3. You've contradicted yourself. No. Can't be true. No solution from there, so that gets us nowhere, actually. Whoops. I said whoops. Okay, that gets us nowhere, actually, but over here we should be able to do something. Do the old square both sides trick. This undoes the radical there, and the 2 squared becomes a 4. And then I need more space, so let's come up here. So I'm going to subtract 4 on both sides, right? Equals 0. There's a quadratic in standard form, we call that. Let's unfoil that puppy. So the x squared becomes an x times x. And a -4, I'm thinking a 4 and a 1, maybe like this. That makes a -4, right? That's a -4. And then more importantly, plus 4x minus x gives me what I want in the middle, of plus 3x. That works, and so we've got actually 2 solutions here, -4, +1. Now let's be a little careful. You gotta always have your antenna up when you're playing around with math. That was a radical equation. Check in the original. That was a radical equation. Whenever you solve radical equations, you have to verify the solutions. Let's try -4. Let's try -4. Okay, so if I go like this, a -4 squared plus 3 times a -4 like this, does that equal 2? Well, that would be a 16 minus 12, which is 4. Radical 4 is 2. That worked. -4 works. Now let's try the 1. 1 squared plus 3 times 1. Does that equal 2? Well, that's a 1 plus a 3 is a 4. Radical 4. That worked too. Actually, they both work. Well, that was nice. They both work. Cool beanie weenies. They both work. So somewhere around the line you want to say x equals -4 and +1. That is our official answer. Okay. How many more of these we got? 2 or 3? 1, 2. We got 2. Okay, 2 to go. Now these become sort of an acquired taste. Now remember reading in that Oakley book the importance of you gotta play with these enough that you begin to internalize the solution process. Now that's work. That's sweaty work. I've often said math is all about time. The only limiting factor is how much time you can put into it, which hopefully sounds like a good thing. For me, it sounds like a good thing. Of course, then you have to give up something. But anyway, so looking at this equation, what can we use here as a definition for u that would make this fairly ugly equation look a whole lot simpler? So again, you're looking for repeated patterns. Here I see a v over v minus 3. Here I see, if I ignore my 3 for a second here, I see a v over v minus 3. There's the repeated pattern. So what do you say we try that? So I'm going to say, okay, I'm going to take this v over v minus 3, give that a new name, call it u. This equation will be, well, see, this is just a u, right? So that's a u that's being squared, actually, plus. And then here's the u, and then notice it's just being multiplied by a 3. So that becomes a 3u minus 10 equals 0. Happy equation. U squared plus 3u minus 10 equals 0. Happy equation. It's a trinomial. Let's try to unfoil that thing. U squared is u times u. -10. I think I want to use a 5 and a 2. I think I want to use a +5 and a -2 to make sure I get a +3 in the middle. Okay, so we've got 2 solutions here, -5, +2. Those are our solutions for the u variable, the new variable u that we made up. But we got to go back and get v, right? So that's where you bring your solutions and combine them with our original definition. So v over v minus 3, that could be equal to u, which is negative 5. Or, and I'll have some space over here, this v minus 3 could be equal to this positive 2. Two things to try, two things to investigate. Coming back over to the left here, again, I'm going to put a 1 over that and look at it with cross products. So coming down this way, v times 1 is v. Going up the other way, negative 5 multiplies a v minus 3. Okay, so if I distribute, I've got a negative 5v plus a 15. If I add 5v to both sides, I got 6v equals 15. If I move this up a little, I'll have space. That's good. So v is equal to 15 divided by 6, and make sure you do reduce. 15 and 6 can both be divided by 3, so we get a 5 halves. That's one of our solutions. V could be 5 halves. That's a 5. What about this one? Again, make that be a over 1. I'm going to go this way. 2 times a v minus 3 equals v times 1 is just v. So I got 2v minus 6 equals v. If I subtract v on both sides, that will become a v. And if I add 6 on both sides, that will become a 6. And so there's my two solutions. I should probably link them somehow. 5 halves and 6. Saving the best for last as usual. What do you think of that one? Okay, scratch your head for a little bit. What we want to do is we want to try to come up with, well, a pattern. Man, this thing is weird. Pattern that repeats. Question mark? What the heck is repeating here, really? Well, there's an x. There's an x. I guess there's that. Here's an x to the minus 2/3, and there's an x to the minus 4/3. My guess is that we're going to want to use one of those as our u. Let's just think for a second. What would happen if I used this x to the minus 2/3? If I call that my u, what would happen if I squared both sides? Over here, remember, you would just multiply your exponents. Negative 2/3 times 2 is this. And that's fortunate. So let me erase this gup here, because it's kind of in the way. It's hiding what I'm trying to show you here. If we let x to the minus 2/3 be u, in other words, we let this part be u, then it turns out this other part is u squared. Woohoo! Woohoo city. So that means we get, instead of x to the minus 4/3, that's a u squared. Plus 5 times. Instead of x to the minus 2/3, I can use a u. And then plus 4 equals 0. There's our new equation. Our new equation is a cool equation. And that's supposed to be a smile, not just a little bit of a wry thing. Or smile. U squared plus 5 equals 4. Okay, factor some more, man. U squared is u times u. 4 is the same as 4 times 1. And if you FOIL that out, you will get a 5u in the middle. It works beautifully. And so we have our two solutions for u, negative 4 or negative 1. So we solved our new equation. U could be negative 4 or negative 1. Don't forget, what we really want is the solutions to the original equation. In other words, we want x. So you take this part here and you unite it with this part here to say, well, x to the, in fact, let me make some space for this. There we go. Get some space going here. So this x to the minus 2/3 could be equal to negative 4, or, and I'll do this way over here, this x to the minus 2/3 could be equal to a negative 1. Question now is how we solve these things. Well, one way to do it, let's see, I've got two ways in mind. I'm trying to choose one. I think I'll choose this one. One way to do it is to say, well, what does this exponent mean? This exponent means that well, remember, it's three parts to the thing, actually. I've got an x that is squared, but it's in a cube root, and I flip it over, right? Three things. Remember these things? Three-part exponent. X gets squared, but it's also in a cube root, and it's also flipped over. Flip, cube root, x squared. That's what that is equal to -4, which, just to be fun, I'll write it this way. Why am I writing it that way? Because now what I can do, and I don't know how often we see this move, but we could just kind of flip both sides of the equation over. So this is cube root of x squared over 1 equals, and that will become a negative, flip it over, -1/4, like this. So I'm just taking the reciprocal of both sides is what I'm doing. Okay, now what? Well, one way to get rid of the cube is to cube both sides. The cube root, I should say. Get rid of the cube root is to cube both sides. So the left side becomes an x squared. When you take a -1/4 times itself 3 times, you get 1 times 1 times 1 is 1. 4 times 4 times 4 is 64. Ouch. Oh, how do you like that? I just got bit. Stupid bugs. Bugs in February. Who'd have thunk? Anyway, x squared equals -1/64. Okay, where are we going now? Well, we want to solve by square rooting both sides. Square root of a negative is going to give us an I. Oh, by the way, don't forget the plus or minus. Put that in front. Plus or minus I, and the square root of 1 is 1, and the square root of 64 is 8. So actually a nicer way to write this would be plus or minus. Well, you could write it as 1/8 I. That looks good. Or if you want, you could write it as plus or minus I over 8. That would be fine. Okay, anyway, we're getting two imaginary solutions to that one. Plus or minus 1/8 I. Okay, now that you kind of have an idea how to approach this thing, right? So I took the exponent and I said, well, what does that mean? How are fraction exponents or rational exponents defined? It's defined as square the x, take a cube root, flip it over. Same thing here. Square the x, cube root, flip it over, equals -1. Try that one yourself. Try to internalize these moves a little bit. And come back in a second, and I'll show you what I get. Okay, so the negative means flip me over. The 3 means cube root. And the 2 means that x is squared. Over here I got -1, which just for fun I'm going to write it this way. You can always put a 1 under. The reason I'm doing that is because now I'm going to flip both sides over. So the right side becomes cube root of x squared over 1, which I can ignore. And the right side becomes 1 over -1, which of course is -1. Cool. Cube both sides. I'm following the same steps, aren't I? Cube both sides. So that's going to become an x squared. -1 times -1 times -1 is 1. Is -1. Take the square root of both sides, plus or minus square root -1, which is I. Plus or minus I. There. 4 solutions. Boom, 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 boom. Putting those together. 4 solutions. They're all imaginary, but they're solutions. Works for me anyway. Yeah. Good thing we have eyes to play with these days, or we would have got stuck early. Anyway, that's our sorry for scrolling so much, but that's our little introduction to this switch of variables idea. It's an extremely powerful technique when you're looking at an equation that otherwise you're like, geez, I don't know what to do. This one, nasty, right? This one, well, I suppose we could brute force that one. But this one in particular, we were really not going to get anywhere with methods that we already know about. So this idea of switching variables is extremely powerful. So the idea, again, is you're looking for a pattern that shows up in 2 spots. In one spot, it's squared. And if that happens, you can rewrite your complicated equation as a simpler equation. A simpler equation in quadratic form is what's happening in this lesson, which can be solved quite easily. Just don't forget to go back and get x. You've solved for u, go back and get x. Okay, that's good.